Hello and welcome back. We're coming back to advanced topics for undergrads, complex integration to find real integrals. I'm not quite sure if I'm on lecture number 5 now, because I'm uploading lectures not necessarily in the order I record them. So this is a real integral to be evaluated, and it's the second one I think that I'm doing, which is of the form some function of sine or and theta, cos theta, from 0 to 2 pi. So the key things there is the function of sines and cosines and the special limits 0 to 2 pi, which indicate that we really need to work with a unit circle. That's very, very standard. So how we do this particular one, we're going to parameterize our integrand around a unit circle centered at the origin. And the standard parameterization for something like this is, of course, z is equal to 1 radius 1, which I'm not going to write, e to the I theta, and the theta will run from 0 to 2 pi. So it will trace the circle in an anti-clockwise direction. Let's do a bit of labeling. So that's 1. Let's call the circle gamma. And if we look at our integral now, we need to swap the limits, of course, will be taken care of because of integrating around the circle. We need to change, obviously, the sine of theta and the d theta. So first, let's get each of these bits separately. dz is equal to I e to the I theta d theta. And let's call that z again. So that's I, that's my z up there, iz d theta. And let's make d theta the subject. So d theta will be dz over iz. And of course we need to change a sine of theta. I'm going to write the sine of theta perhaps here, and after I change it, I will remove it. We've got the sine of theta is, of course, when written in terms of exponentials, as 1 over 2i e to the I theta minus e to the minus I theta. That's merely, all it's actually saying in there is that the sine of I theta is, of course, I times the sine of theta, and therefore the sine of theta is 1 over I, okay, the sine of I theta. So this a half with this quantity here is the 1 over I is already there, is the a half from the sine, and it's merely that. Okay, so we can actually do better than that, because it's best to move it into z's. So 1 over 2i e to the I theta is, of course, z, so that's z minus 1 over z. So let's put things in, and we're gonna go now around gamma, close path, and what are we going to get? 1 on the top. We got the 5 plus 4 lots of this quantity here. So this is where I normally make loads of mistakes. So 1 over 2i z minus 1 over z. If you cannot see what I'm writing, I'm going to move out of the way because I need to check myself what I'm writing. And my d theta is dz over iz. And let's check that I haven't missed anything like I normally do. First of all, my d theta is dz over iz. That's correct. And my sine of theta here is 1 over 2i. The 4 was already there, so I think I've done everything okay. I haven't missed anything, signs or factors of 2 that I often do. Okay, we need to simplify this a little bit further. Shall I just do it as it is in there? I have to be extra careful. So first of all, times in the iz with the 5 is going to give me 5iz. And now I'm going to times the iz at the front and leave that on the next line, perhaps to simplify. So this is z minus 1 over z. This is my dz. So I need I. First of all, there's going to be a z in front of it, or I'll write it at the back. So this is z, and this now I will cancel this I into real, and I'm gonna have a 4 over 2, which is a plus 2. So I hope there's no mistakes in there. It will come out in the wash. So hopefully this of course got nothing to do with it. Was like the general form of this integral, so it's it shouldn't really interfere with our workings there. Multiply it all out to see what we're going to get. On the denominator we're going to have a 5iz plus we got 2z squared, let's not forget the z at the end, plus 2z squared, and then this will cancel and it will give me a minus 2. And this is not really nice. My brain is not up to doing things like that at this moment in time. 2z squared plus 5iz minus 2, 1 dz. What do I need to do next? Okay, what I need to do next, do I need this quantities here? I don't think I do, but I will leave the circle up there. So by the residue theorem, what we've done so far, we changed something from an integral on the real axis, or the theta axis if you want. We changed it to an equivalent integral in the complex plane. Okay, I didn't put all my gammas all the way through, but that's not essential, it's just a little detail. Let's do that now. So we moved it into an integral on the complex plane, and I know this particular integral by the residue theorem, its value is 2 pi I times the sum of the residues of f of z. I will define f of z because I didn't write it there. Residues of f of z inside gamma. So what is f of z in this particular case? Well, f of z is any of these quantities in here, of course, including that bit there. So you can think of it in this in the very last line. F of z is this function here. Okay, but this is our f of z. So we need to find the residues of the poles of f of z which lie inside this particular curve. And in order to see what poles we have, we need to factorize this denominator, which got that I factor in there, which is going to make life a little bit hard. We can use the quadratic formula. I doubt if I will be using completely the square. Normally I'll do that by inspection. Let's hope I don't shame myself here. I'll try inspection, because I can kind of see the numbers, but it's the eyes that cause problems because they reverse signs and things like that. So it's a 2z with a z. I got positive on the iz's, so but negative there. So there's got to be probably i's here. And in order to get the 5, I need a 2 there and a 1 there. So it's going to give me, let me just check the numbers first of all, and I'll worry about the signs at the end. So this is my 2z squared. I've got 4zi. And iz gives me a 5z, and I think I times I will give me the minus, which means these two things were in fact a plus. I think this is correct, but let me just run it through once more, just in case we're doing stupid things and all our work goes in vain. To the square z. Yeah, I think that's correct. Okay, so I'm going to write it once again. So this is now the integral of around gamma of 1 over 2z plus I. So this is this denominator, of course, factorized, z plus 2i dz, and take these brackets away. It's going to be 2 pi I times now where do we have poles? We have obviously simple poles. One is at negative 2i, that is outside my circle, it's somewhere here, let's say, and I couldn't care less about this one because it's outside my gamma, but I have one which is at negative half I. This is inside, somewhere here, minus half I. So I need to find the residue of this particular pole in order to put it here. So it's just a single quantity that I'm after. So let's make some space. I'm going to rub off the very top line in order to compute the residue. So we're using, of course, the standard formula. Most of the time, the standard formula, because they're normally simple poles, is very, very efficient and very quick. So in order to find the residue of f of z at minus half I, this is the limit as z tends to negative half I. So that's z plus half I times f of z. So in our case is the limit as z tends to minus half I. And I'm going to put my f of z, of course, in factorized form. We have to be careful because there's a bit of an extra factor here that we need to take care of before we cancel any brackets. Normally in this formula there'll be a cancellation. And let me just make a little bit of room here. I'm going to write this one first. This particular term does not cancel, but this z plus half I will cancel part of that. So we need to factorize a 2 out of this bracket. I'm going to stick it in the middle somewhere. And if I pull out a 2, it's going to give me, of course, an identical bracket to this one, z plus half I. And this will now compute my residue, because of course this bracket will cancel this, but I still got a 2 in there. So the limit now can be found very easily I say, but brain is not is misfiring at the moment. So I need to put minus a half I in there. So that's going to be a 1 on the top. Minus a half plus 2 is plus 3 over 2. Plus 3 over 2 times 2 is 3i at the bottom. And hope I haven't made any mistakes. Okay, so that is the actual residue of the pole at minus a half I, which now is the missing number that I need to put in there. And this is actually rather nice because, of course, the i's will cancel. So the answer that I'll get for this is just 2 pi over 3. Is this my answer to my integral? The answer is yes, indeed. Let's just check what we've just done. We transformed this particular integral, which was 1 over 5 plus 4 sine theta d theta, from the real line into a complex integral around a unit circle gamma, which has this form, some f of z, some complex function dz. We know how to find the value of this complex integral by the residue theorem, and this turned out to be, of course, 2 pi over 3, but of course that's the answer to the real integral that I was trying to find in the beginning, and my work is done. This one was a little bit messy with the numbers because the sign has these i's all over the place, and the denominator was a bit of a pain to factorize. If you couldn't do it, of course, but by inspection you get more complicated things, please use the quadratic formula or something like that if you're faced with a scenario like this. Okay, I hope you find it useful and stimulating, and who's laughing now? I certainly am. See you very, very soon.